The 15 waiting, 15 people are there. Okay. Hello everyone. I think we are on for our live session. I see here 15 people waiting. We are on. So this time we are trying a new thing. I mean, last semester onwards we started this online live session activity. Of course, it is primarily to interact, to see if you have any questions. What is possible to answer, I'll answer here. If it's not possible, I'll make a note of it and I'll try to put it up in the discussion forum. That's just the introduction. If you have any questions, you are welcome to start asking questions, comments, anything you wish. It's an opportunity to chat. I can give you some background on how this course came about, so that you get some sense of what it is that we have put together here. So, as a student, I have had solid state physics courses that I have taken, and I've had some version of it during my undergrad days. I've also had some version of it during postgraduate schooling. In both cases, I found that the books that they use are actually good books, but at a very high level, or at least at a level that didn't immediately intuitively make sense. It was very difficult to find a book at the right level. Either they were too elementary, or they were or they assumed that you already knew a lot of stuff. So, therefore, it was always very difficult to actually understand the topic to any reasonable degree. So it is in that context when I got an opportunity to teach this course here at IIT Madras. I took it on to see what best I could do to correct that situation or to remedy that situation to whatever degree that was possible. And a lot of effort has gone in to pull those lectures together, those 40 lectures that you're seeing through this course. Several years of work. I don't know how many books I have referred to, obtained a lot of books, search for a lot of information online, etc. And of course, I had to make a lot of, put it all together, make sense out of it. So that took quite some time. And at the end of it, what I put together class by class is what you see in that sort of the set of lectures that you see. So it's been a pretty long journey, I would say. In my view, in fact, once this, as you see through this course, I believe any engineering student would find it a distinct step forward. Any person in engineering can access this course, and if they go through that course, if they just follow the lectures, lecture by lecture, attend to the topics, try to understand the topics. I think it's taught at a level and explained at a level that at the end of the course, you will have a significant step forward in terms of your understanding of what is where, and also your ability to access a much higher end book, let's say something like Ashcroft or Anne Berman or something like that. And so that's sort of the intent. And I think once you do this, you can actually go to any solid state physics course anywhere, and you should be able to, at least you won't feel lost. I think that was my urgent goal, so to speak, as a faculty. I wanted to make it such that student taking this course would not really feel lost. So that is what I aim to do, and that is basically what was done as I put this course together. I have also, based on exactly this course, it's an NPTEL course, and based on the NPTEL course, there's also which has been put together based on this course. So I can just show you a copy of the book while we are still waiting. So this is a copy of the book. If you're interested, basically this is the same content that you're seeing in the course, so you can actually just follow the course. You can look at the handouts in the course and so on. It's been put in book form. Many more questions and worked examples are available in this book, and also the DVDs of the lectures are available in the book. I think, yeah, there you have. There's some DVDs. 2 DVDs come with the book, which have all the lectures. So if you would like a copy of the lectures for yourself, then this is a reasonably easy way for you to do it. You can just get this book. It's very nominally priced in any of the online retail places. Of course, it is basically all based on the NPTEL course. It is a straight out the NPTEL course. with some add-ons in terms of, there are worked examples, there are additional questions, and also there is a lot of what should I say, animations associated with the course, which are present in this book. So if you are interested, it's exactly titled as the course is titled, Physics of Materials, Essential Concepts of Solid State Physics. So this book is available, and you can take a look at it if you so desire. So that's something I wanted to share with you, and I believe, that it is a useful addition in case you're interested in looking at this kind of a topic in greater detail. Okay. I see here Nikhil Sen has a comment. So I think we are on. I'm hoping that you are in a position to see live and also ask questions if you wish. Questions or comments. So, in fact, incidentally, we are right now sitting in, just for your, just to give you some frame of reference, we are sitting in the NPTEL office. We usually do this off of a separate room. So you may hear a little bit more background noise, but that's because we are sitting in the NPTEL office. And part of the reason was we had some connectivity issues. And that's the reason why we came to the NPTEL office and reset this up. So I'll just say something here. So feel free to ask any questions. I'm logged in, and we'll try to answer. So if you want me to just go over the flow of the course, then the course is something like this. So if you look at the flow of the course, we have some introductory material on what the materials are, what materials scientists use and how they use it, and so on, how the materials are studied. And then there's something about how you model a material. So that's something you've already seen. We look at different properties of materials, at least at an introductory level, just to set some stage for the discussion. So we look at chemical properties, mechanical properties, thermal properties, electrical properties, magnetic properties, optical properties. So this we do as an overview to understand what is possible with the various properties. And then what we have done is we have looked at thermal expansion. So that is a property that I felt could be handled in a single class. So in the course of a single class, we explain the property. You get to see, how that expansion happens. We look at various possibilities of it, and we build a model. We build a model which tries to explain thermal expansion from basic first principles, so to speak. So that we do. Then we get on to electrical conductivity. We try to get a sense of what is possible with respect to electrical conductivity, and also more specifically how it is measured. That is more as a sense of, for a sense of completeness, to understand how it is measured. What are some issues associated with measuring it? I wanted always to have a good grounding on something that we can physically see, we can physically measure, feel, whatever it is, relate to, rather, I would say physically relate to. So that's something that we have tried to. Okay, it says here, I cannot see or hear anything, it says. Okay, I'm able to see here, no? That means it should be on. Okay, now he can. Okay, so I was just going over what we are doing in this course, so I'll just do that. That will set you some context for the discussion, so to speak. So electrical conductivity is something that we look at. We look at AC measurements, we look at DC measurements, we look at 2-probe measurements, 4-probe measurements. So that's something we do. Then we get on to this free electron gas and the ideal gas. We talk about the ideal gas. We basically want to understand what the ideal gas behavior is, which we already know from school, but I wanted to make that complete because we essentially take that same idea and put it, impose it on a electron, on a set of electrons in a solid. And that's the way, many of the modeling activities go. We take some idea which we think works in some case, and if we see enough reason to believe that the same idea can be utilized elsewhere, then we actually directly try and utilize it. And this is the reason why, when you do this, the reason why you will find people who are physicists and who end up working in the stock market. You would wonder, what is the relationship? But the relationship is that, the kind of math they do, the kind of analysis they do, is actually, there are enough similarities that, even though they may be doing high-end physics, and regrettably, maybe they don't get a job, they can end up working in the stock market, analyzing the data in the stock market, and that would still be something that they could usefully do. So that is some activity goes on. So the same concept is being used here. We take something that is familiar for us as an easy model to build, which we build using the ideal gas, and then we just assume that, let's assume to start with that all the electrons in a solid behave like ideal gas molecules. We simply impose those properties on that gas, and then we build it. So that model gets referred to as the Drude model. So that is what we discuss as we get into the course. So we discuss the Drude model, and so that Drude model which assumes that these electrons behave like ideal gas atoms, then is in a position to predict what is the electrical conductivity of the material, what is the thermal conductivity of the material. So this is what we do. So we do this calculation. We figure out what is the electrical conductivity, what is thermal conductivity, and there is something called a Weidemann-Franz law. So we compare the thermal conductivity to the electrical conductivity, and there's a constant. We try to see how well it matches. Because in all these cases, that's the idea. We want to have a theoretical way of doing something, and then we want to check whether the theory is correct. I think in the early part of the course, I mentioned that, and that's something that I will again say is ultimately the theory is good only if it matches experimental data. If the theory doesn't match the experimental data, it does not matter how sophisticated you think the theory is or somebody else thinks the theory is, then something is missing in the theory. May not be that the whole theory is wrong, but some detail is missing in the theory, which is why it is not matching experimental data. So you have to find a way for it to match experimental data. So if it does match experimental data, then you've got to go with it. Then you can say with confidence that you have done something nice. So anyway, so that is why when electrical conductivity data matches up and thermal conductivity data matches up, and then you do this Weidemann-Franz law matching up, it gives you greater confidence that the Drude model is doing something right. And then we look at the Maxwell-Boltzmann statistics. Mainly, we take into account the fact that when we talk of ideal gas atoms, they are assuming some behavior for the gas atoms, and that behavior is represented by this Maxwell-Boltzmann statistics. And that is basically the statistical approach is generally used for any large collection of particles where it doesn't make sense for us to go and get the property of every individual particle, then do the average for the whole system, and then figure out what the property of the system is. It is not physically feasible for us to do that. Therefore, we do a statistical approach. We make an approach where some approximations are made for the system, we understand the system, and on that basis, we build this idea. So that is how we get the Maxwell-Boltzmann statistics. And we see what it predicts in terms of how many, what is a macro system, what is a micro system, and then what happens, a number of systems, number of states that 3-particle system has, a 4-particle system has, something like that we start off with, and then we go to a large particle system. And it always uses this idea that in statistical mechanics, something that is the equilibrium state of the system is only one probable state of the system. So that is the point that we try to convey in that statistical mechanics, that it is just one of the probable states of the system, which is the equilibrium state. It is just that it is going to occur so many times within the context of the possibilities that effectively when you measure the system, you will only find this. Okay, so it will occur more often than all the other possible states of the system combined, and therefore you will only find you'll effectively find it. So that's basically the idea of the statistical mechanics. And Maxwell-Boltzmann statistics is one implementation of that analysis of that situation. Questions on the floor? Okay, we do have some few questions here. I will try to answer them as we go along. So let's see here. Um, okay, so we have a question from Aniket Patil. Aniket Patil has a question here on application of physics in okay, so physics is used extensively in the automotive field. A lot of, I mean, in many ways, there is no, I mean, where physics is and where thermodynamics, there's no strong end for physics and no specific place where physics ends and thermodynamics takes over. They're all interrelated fields. So we use a lot of physics in the way in which, let's say, the material systems inside automotive vehicle work. So, for example, a lot of material science that goes into oxygen sensors in a vehicle utilizes the physics. Okay, so what is the physics there? So you have a material which has oxygen. It's an ionic material. So let's say zirconium oxide. So zirconium oxide is there. You have oxygen there, ZrO2. So you have O2 there, and just because of thermal equilibrium, because of the temperature of the system, you will have a situation where you have some number of oxygen ion vacancies. So all that, writing the equations for those oxygen ion vacancies, the defect structure of that material as a function of temperature is physics. And then similarly, if you dope the system with some other dopant, in this case, the dopant is not in the same context as a dopant in the semiconductor industry. In the semiconductor industry, we put dopant and we're talking of charge carriers for electronic conductivity. We say N-type, P-type, etc. Right? So this is not dopant in the same context. It is essentially an ion for an ion, right? So you can put, instead of when you have ZrO2, in some places you can put, say, instead of Zr, you can put cerium, for example, okay, or yttrium. So something where when you look at ZrO2, Zr is 4 plus and oxygen is 2 minus. So 2 to O2 gives you 4 minus. So that is how the system is charge neutral. So now if you take that system and you keep it in at any temperature, let's say it's at 60 degrees C. Just because it is not at absolute zero, you will have some number of defects in it. In this case, those defects are point defects, which are either zirconium atoms not present in the zirconium sites or oxygen atoms not present in the oxygen sites, or ions. Okay, zirconium ions not being present in zirconium sites, oxygen ions not being present in oxygen sites. Due to this absence of an ion, you give the possibility of an adjacent ion jumping across to that location. So you may have oxygen ion present, one vacant site, another oxygen ion present. So you have an option that this oxygen ion can jump this way and that vacancy can jump the other way, right? So in this process, you enable the oxygen ions to move across the system. Now, if you have a gradient, if you have more oxygen on one side and less oxygen on the other side of the same zirconium crystal, then using this hopping process, you can slowly get oxygen to diffuse through the system. Okay? So that is how it happens. Now, generally, if you also put electrodes on it, simply because you have oxygen of one concentration on one side, oxygen of a different concentration on the other side, you can get a potential difference, which you can measure. And if you know enough of the experimental data you collect, enough of the science of that system, you can actually relate the potential that you measure to the difference in oxygen ion concentration on either side of that zirconium material. Okay, so this is how oxygen sensors work, and that works basically because of an understanding of the physics of that system, or at least we are able to figure out how it works because of our understanding of the physics of the system. So how is this used in an automotive sector? In an automotive sector, what we do is, see, they are always trying to make the car more fuel efficient. So how do you make it fuel efficient? And why is it, first of all, fuel inefficient if you don't do anything? So what happens if you compare olden days cars and how they function? When you press the accelerator or you press the brake, etc., certain amount of fuel and certain amount of oxygen goes into the engine, and then it burns, and that's how you get energy. So in older cars, they would just have some standard meter. So they would keep sending in some fuel, some amount of air, and it would just burn. Now, this means sometimes it is putting more power than you need. Sometimes it is putting less power than you need. So it is not a very smooth, delivery of power to you based on what you are trying to do. It is not the best possible combination of fuel and air. So the way they make it efficient is to set it up such that all the fuel completely burns. That is when you have not wasted the fuel. So how do you figure that out? You figure that out by checking what is the oxygen ion concentration in the exhaust fuel. Okay, so the exhaust stream, what is the oxygen ion concentration? So if you want to just about, you basically try to set it up so that you have completely exhausted the fuel, and then you have remaining oxygen. So now it is called burning with less amount of fuel and more amount of oxygen, and we use the exhaust sensor to figure out what is the partial pressure of oxygen in the exhaust stream. So for that, we compare it against air, and that comparison is done using this zirconium crystal. So you have air on one side, you have the exhaust stream inside it, and then you compare the two, and so you see what is the potential difference. If you see more fuel coming in the exhaust stream, you immediately increase the amount of air going into the engine. Okay, you see, and so correspondingly, you can adjust this. You can adjust this such that you're always at just about burning the entire fuel. So this is a example where the physics of the system is understood, and that is being used in the automotive sector. Okay, so that is one example. Let me look at how is. Okay, something about multifunctional materials, which can be used for different applications. Okay, so multifunctional materials. Again, I would give, in fact, a good example. It just so happens that the previous question also related to zirconium, so I'll use zirconium as an example for this. If you take zirconium, it is actually a material which has a wide range of properties. So you can use it for biological applications. So if you go to dental applications, they use zirconium for say tooth replacement. So artificial teeth are actually made of zirconium. So that is something that is there. Similarly, you can have, for example, this oxygen ion sensor. You can have it as a jewel. So, for example, in India, we use this term American diamond, right? So we use that American diamond term. In fact, if you go to America, nobody uses that term. Nobody knows what is American diamond. But what we mean by American diamond is actually this zirconia crystals. Single crystal zirconia is called an American diamond. It can be cut into that shape, and it has all those reflective properties. And those properties. And if you actually dope it, you can actually get it in red color, blue color, whatever. You can get different colors. So you can use it for cosmetic applications. So you have oxygen sensor, you have dental application, you have jewelry application. You can also do some of these MOSFET kind of devices where field effect transistors, I think they're called. So there's a place where you put a potential and that controls how much current will go through that device. And that is again something which you can do with zirconium. So right there is a range of applications that you can put the zirconia to. So it's a very multifunctional material which can be used for a number of different things. Let me see if I get this two questions. Understanding of Maxwell-Boltzmann. Okay, so there is a question from Nikhil. In fact, yes, Nikhil, who is online. Yes, he has a question here on full understanding of Maxwell-Boltzmann and Fermi-Dirac statistics. Can you suggest some online resources, text or video or book? So, of course, this online course we have itself has some videos on it. The same thing in text form, possibly with some worked examples, is what I just showed you. This book. It's the same thing. It's the same lectures that you're seeing, but it has been converted to a book form. And maybe if you read it as text, perhaps it will convey that idea to you better than if you saw it on a video. So you're welcome to take a look at it. It's the same title, The Physics of Materials, Essential Concepts of Solid State Physics. So this you can get it straight off of our NPTEL course. So that's something you can get, and I think hopefully that will help you understand this issue. Simulation. Okay, so I think there is interest in having some more challenging problems to try out. I will try to add some challenging problems. We have been busy with some other recording. There's another course that is being recorded simultaneously, and so some of these assignment questions have been put together before that. I have not had an opportunity to add additional questions to it. I will try to add something which is a little bit more significant, which will require you to do more involved calculations. So I will do that. I have not done that so far, so I will try to do that. Let me see here some more questions here. What will happen is, can you please explain the? Okay, so there is this question from Shamal Mukherjee, Shamal Kumar Mukherjee. So, in fact, it's I think a question he had asked in the forum also. Can you explain the ellipsoidal constant energy surface for indirect semiconductors like silicon or germanium? Okay, so I have not really gone into the detail of specific semiconductors band diagram. So, I think that is what is being referred to here. What is the relation of those ellipsoidal surfaces with the Fermi surface? So I'm not really sure what this is referring to, but my guess is that it refers to the band diagram and features that you see in the band diagram. So one of the things I will tell you is, as the course proceeds, we come up with those band diagrams. We do come to the band diagrams. We do draw those band diagrams, direct and indirect band gap semiconductors. So that is looked at in the course. And in fact, you draw the E versus K relationship. You see how it interacts with Brillouin zones. And at the interaction, and at the okay, I'll come to that. So at the interaction site, you get all those distortions, and therefore the band diagram. Now, the point is that the Brillouin zones are different in different directions, or crystallographic directions, and therefore the band diagram that you draw in one direction is not exactly the same as the band diagram that you would draw in another crystallographic direction. So if you take, if you just go and you look for a band diagram of silicon or germanium or something like that, then what you see is you will see a series of curves which start off at different locations and then go in different directions and so on. And that is basically what they have done is they have taken a wide range of crystallographic directions that are considered important, and in each of them they have looked at the band diagram, and they have tried to put that all together in a single sheet of paper. So that is why it kind of looks complicated. You see these curved surfaces in various different directions, and there is some notation there which tells you from where you're starting, which direction you're proceeding, what is the band diagram you're seeing in the direction, and then from that location you go to another location, what is that band diagram that you see. So you will see some vertical lines, you'll see some curves and so on. And so that is how that band diagram comes. So if you want to understand a specific band diagram, so let's say a silicon band diagram. So I think here, for example, talking of silicon and germanium, if you're looking for a specific band diagram and you want to understand it, you really have to go back and check the directions and go over it in that systematic way. Actually, some of it I do in one of the classes in the book. Let me just see here if I have got something specific on it. Yes, I do have in the book, which is not actually there in the course. In the course, we don't directly do this. I do have a section in chapter 14, which is on conventions regarding representing band diagrams. So in that, we do have all the for the various lattices, what is the convention that is used, which direction it is plotted. So something like that is given. So if you actually look at it, there is so based on this you can at least get an understanding of how that band diagram evolves, or at least how it is being represented in that site. And so that is, I think, what you need to check if you are really looking for a particular band diagram and you want to understand what is a feature on that band diagram. You have to really go back and check the crystallographic directions and understand E versus K in that context, and then put it together. So it's a little bit more involved. We are not going into that level in this particular course. I have not taken a specific materials band diagram and explained it in full detail. So maybe I will try to put something project preferably related to semiconductors can be used. Okay, so that's again something I will get back to you. I don't have immediately offhand. I don't have a specific design or simulation project that I can immediately give you. I will try to get you something which is something that you can run on MATLAB. I need to check a little bit on that before I can put together something that's reasonable that you can try out. That would be interesting, but we'll try to do that. Okay, so So that was, I think, some of the questions that we got so far. So I'll just continue a little bit and tell you what else we are covering in this course, so that you get a sense of. So we are looking at the statistics. We look at quantum mechanics, why it comes about, how it comes about, Fermi-Dirac statistics. Then we look at the idea of anisotropy in materials. The fact that for the most materials that we're going to get, at least crystallographic materials, crystalline materials, we're back. I'll just join you in a moment. Just looking through some of those questions. Yeah, so we look at anisotropy in crystalline solids, and the idea of confinement, and what is this idea of confinement, and how confinement results in this quantization of energy, which is what we end up, which is what we end up seeing when we see the band diagrams. So quantization and confinement. So that combination we look at. Once we understand that, then you understand this density of states, and then we also understand all these things like Fermi energy, and we finally get a handle or a understanding of the electronic contribution to specific heat at constant volume. So this set of phenomena we are able to pull together once you cross that level of understanding. So we look at Fermi energy, we look at Fermi surface, Fermi temperature, we look at how you can estimate electronic contribution to specific heat at constant volume. Then we look at reciprocal space. So actually, yeah, we come to Brillouin zones a little later. We come to reciprocal space. We try to understand what is reciprocal space, what is that notation, and we go through an exercise in that reciprocal space process to make ourselves comfortable with that notation, to make ourselves aware of the notation, use the notation, and understand what it does. And then we talk of Wigner's heats, cells, Brillouin zones, and how the bands originate. So once you understand the confinement, you understand the E versus K, you understand the Brillouin zones, you understand the structure of the material. So then we are able to pull all these together, saying that when the wave-like nature of the electron interacts with the periodic structure of the material, then you get the band diagram. So that is how you get the band diagram. So that's what we talk about. We also do an analytical way of doing it, of doing the calculation. We do the calculation just to understand how that pulls together. And so we actually have a calculation which, even though conceptually I show you how the E versus K hits the Brillouin zone, we also have a way in which we can do analysis based on whatever people have already worked this out, where you will find some relationship. We will come up with a relationship. We will build an equation where there's something on the left-hand side and something on the right-hand side. And the point is, you will have a trigonometric function on your left-hand side, and you have some expression on your right-hand side. Now, based on the values you select for the expression, for the various parameters of that expression, you will find that there are conditions under which the right-hand side of the expression will give you an answer which cannot be satisfied by the left-hand side of the expression. So we interpret that inability of the right-hand side to match the left-hand side as an indication that those are conditions that are not allowed in the system. Okay, so we write an equation which develops based on the basic understanding of the physics of the system, and then we have some trigonometric function which, for example, should be between plus and minus 1, and then you have some expression on the right hand side which has energy as one of the parameters. Now the energy clearly as a variable, so you can change the energy. Now you will find that at some values of energy you will get an answer for this expression which is more than the plus or minus 1. So we say that those energies, we interpret that to mean that those energies are not allowed in the system. Then there is a whole range of energies for which it stays between the 0 and 1 range, and therefore those are allowed energies. So that is how we say that this set of energies allowed, it's an allowed band. This set of energies not allowed, band gap. Again, a set of energies allowed band, and that's how we do it. Okay, so we can actually calculate that. So we do in this course and in this book also, we do both conceptually in terms of E versus K, in terms of Brillouin zones, and in terms of a diagram that we draw where the E versus K is a curve, and then you have all these Brillouin zones, and then you see it. And we also do that in 2 dimensions. We do that in 3 dimensions. And in the book, you also have the in 3 dimensions, which shows you how the band happens, how the E versus K relationship distorts as it comes near a Brillouin zone. And then, so that we see as a concept, as something that we see in a figure of that sort. And then when we actually do the calculation, we see independent of from a physics perspective, and once the calculation is done, you'll get to see how that band evolves, at least with respect to that calculation. Then having come that far, we also very briefly we look at tight binding approximation. But having come that far, we use those theories to explain various material phenomena. So what are the material phenomena? We look at the semiconductors, we look at optical properties of semiconductors, and we look at the phonons, we look at magnetism, and we look at the electron quarks. So these are all various phenomena that are there in the physics realm of physics that we tend to utilize, and all the theories that we have developed up until this point. So which is a fair bit into the course. So I would say in the last quarter of the course is where we come to this, where having developed all those theories, we see phenomena that we are aware of, and we see if the theory is able to help us explain this phenomena. And it actually does a very good job of explaining those phenomena, and that therefore gives us confidence that we have understood the phenomena. Then we finish off with 2 topics, which is superconductivity and Bose-Einstein statistics. So through the course, you look at Maxwell-Boltzmann statistics, Fermi-Dirac statistics, and Bose-Einstein statistics. So 3 statistics we look at. So that statistics is covered in this Bose-Einstein statistics. So so it relates to our so let's just see here. I'll just tell you a quick thing on it before we move forward. In just a moment, we'll look at that. Yeah, here we are. We are at that. So, of course, it is. Sent this out for publication, and it did not get published. And he still felt it was something useful, so he sent it out to Einstein. And fortunately, Einstein had the time to look at it, and then he sent that out as as an enhanced paper. He came up with some interpretation which spoke about a Bose-Einstein condensate, and then that is something that was proposed. So incidentally, this was proposed quite a long time ago. This was early 1900 work, 1924. Because this prediction was made, Bose-Einstein condensate, and I think only in the 1990s or something like 70 years later, they managed to actually physically make that condensate, because it needs extremely low temperatures. Extremely low temperatures means you're looking at a temperature less than 1 Kelvin. Not just less than 1 Kelvin, vastly less than 1 Kelvin. You're looking at 10 power -3, 10 power -4 Kelvin, almost at absolute zero. And only under those conditions, those atoms actually condense down to this thing called the Bose-Einstein condensate. So it's a very interesting phenomenon. At the end of the course, we look at it. We also see that in the context of the superconductivity and so on. And finally, we finish with some physics of nanoscale materials. So we understand the nanoscale material, what is unique about the nanoscale material, and how we can, explain the behavior of a nanoscale material using the physics that we have understood up to that point. So that's sort of the range of things that we'll do in the course. Of course, some of these questions I have looked at. Let me just see if I have missed something here. I will try to catch you on that. Convey that to you. No, I think we sort of did most of this. Let me just see if there's anything else. So the only thing I will ask you, I'll encourage you to do is also to, in my opinion, it's a fairly involved course. It takes some time to go through it, but at every stage, I believe the content of the course is something that a reasonable engineering student should be able to follow. Not a problem, in my opinion. So therefore, I encourage you to talk to your, if you have other classmates who are also taking this course, I would encourage you to tell them to stay on the course. So, keep submitting those assignments. Don't worry too much. If you have questions, you ask. If you're not sure, you ask. No problem. But stay on the course. Stay on the course till it ends. I think you will find it reasonably productive. And it helps if you are liking the course and if you are enjoying it. It helps if you can convey that to a few more students. Then they will also feel a little bit more confident. I think this topic is like that. It is easy for students to sometimes get scared by the topic, and so peer help helps. So please don't lose out on it. Please try to help your friends stay on the course. And also use the discussion forum. Please feel free to post on the discussion forum and discuss various things in the forum. The forum is not intended only as a you ask a question and I give an answer kind of thing. That is not the intention of the forum. Although many times I think that's how we start out. Feel free to ask a question, and if somebody else asks a question, feel free to answer it. We will be watching it, and if the answer is fine, then it's fine. And if not, I will try to intervene and give you some additional information, or maybe I may give you a different answer. It may not necessarily mean your answer is wrong. It may be a different perspective on the same idea. So feel free. Don't feel shy or diffident on the forum. I do know that a number of you do ask questions, but you can keep it more active. You can ask even more questions as we go along. But more specifically, as I said, please try to encourage your friends to stay on the course. So that is, I think, one thing I wanted to convey to you. This is a course which we have actually offered after some time. I offered this as an online course maybe 2 years ago. After that, I have not offered it as an online course. The content is there on our NPTEL site, but as an online course, I'm offering it again this time. So it's been a while. We'll try to offer it once a year. It really depends on how much of interest is there in the course and how many people are keen on following through the course. So that's why I also feel you should try to see if more of your friends can stay on the course and keep submitting assignments. So that would be really useful for them as they go forward. So I think that is what we have. So there's a question on format of the final examination. Yes. So format of the final examination will be actually the paper is ready. In fact, so paper is ready for the final exam. It will be multiple choice, but there are problems. So there are a few questions which are problems, which are sort of like connected problems. So there will be like say 3 or 4 steps in the problem. So I will have a problem statement, and then I will have 3 or 4 steps. Each step is a question. Okay, so maybe you have to calculate something out, and that's your first answer. That answer you will use for the second question and third question. So something like a linked question. You will have a few of them. So you will have what we try to do in the NPTEL process is to have some number of questions which are sort of recall from the course. So maybe 25% will look very similar to what you have done in your assignments. 25% will be of similar nature but new questions, and then 50% will be relatively new questions. So we have some range of questions there. So again, that's something that you should feel confident about if you're answering the assignments regularly. And for the assignments, although you should try and do it yourself, we are not explicitly forbidding you from discussing with your friends and submitting assignments. We would like you to submit your own assignment, but you are at least welcome to discuss with your friends to understand the question, to make sure you're not missing anything. In my opinion, the assignment is kept relatively simple in this course so far, mainly because I find that given that the material itself is a little bit heavy, starting off with the heavy assignments and keeping little heavy assignments may get very few students to stay the duration of the course, and therefore they would lose the benefit of the course. So therefore, the assignment is kept relatively straight from the lectures. So you can in fact watch the lecture, do the assignment. It will be very straightforward. You should be able to do that. And if you do that, you already have 25% marks because you have done the assignments. And then about 25% of the final exam is going to be very similar to this. So if you do your assignment regularly, you have a reasonable chance of getting your 40%, which is the minimum that you have to get a NPTEL certificate. And then over and above that, if you do well, if you cross 60%, you're going to get a elite certificate. If you cross 90%, you're going to get a gold medal certificate. So the last time I offered, there were people who got those elite certificates and gold medal certificates. So the final exam does set a little bit of a standard so that everybody has a chance to do and show what it is that they have learned. But if you do your assignments regularly, getting a certificate from us from the NPTEL process is definitely doable, even in a course that is as fundamental as this. It is not. It's not the same as soft skills course or something like that. It is a much more involved course, and therefore it does represent a level of challenge. But you can do it, and it is perfectly doable. So again, I encourage you to stay through the course, submit the assignments, and take the final exam. I think you will enjoy it if you just go through that process. So I think that's what I wanted to convey to you about the examination. Okay, there's some question on registration. We will get our staff to answer about that on the registration process. So let's see what is how many.
He didn't enroll yet.
Oh, he's not enrolled. So okay, so if you have not enrolled for the course yet, then you will not be able to register. So if it says here as it says you're saying that it shows that you have not enrolled for any course. In case you have not enrolled, if you have not enrolled for the physics of materials course, then you will not even be able to register for the examination. On the other hand, if you have enrolled and for some reason it is showing an error, then please do contact our office or you please send us, you can post on the forum, you please send me a question on the forum, I will get one of, or you, then I will be able to forward it to our office staff and they will address it. So if you have enrolled and it is not allowing you to register, then that's something we look at. But if you're not enrolled at all, then it is a bit too late. You will not be able to do the registration for the exam at this point in time. So there's a question by Pushpendra that he's in high school now and can he explore the course without giving examinations? Absolutely, you can. You can see all the content of the course. You can even try the assignment for fun. All the assignments are free. The entire course is free. All the assignments are free. You will get your assignments evaluated for free. So there is nothing, no pressure on you. Feel free to do it for fun. Enjoy the course and submit your entire all the assignments and go through the entire course. You don't have to give any examination. It is not at all necessary. No no mandatory rule that you have to take the examination. So you can do that for fun now. Later in future, if you suddenly feel that you want a certificate, you will have to take it the next time though. You will have to enroll for the course the next time it is offered. And at that point, you can actually register for the exam and take it. But you can actually submit assignments now, and let's say at some point you feel confident that you can take the exam, and if it's still available for registration, you can register for the exam. But it's not necessary, so you can do that. Okay, Tirumala Devi has asked, can a student open assignments and answers after completing the course? So let me check on this. Okay, I think let me just check on this one moment, and I'll tell you if an enrolled student can do that. I'll just give you an answer for that one in just one moment. Okay, so I think the answer is coming up right now. We are getting it typed up and it will be up on your screen shortly on what degree you can access this. The content you can always access even after the course is completed. But whether you can access the assignments is something that I'm just trying to get that figured out. We'll have that answer up for you in just a moment. So, but all the content you will be able to see at any point in time. As I said, it is even archived on our NPTEL site, so you can see it at seeing the content is not at all an issue. You can see it at any point. We'll check on the assignments. Okay. I will answer, but no problem. I will not solve it. They want to know if they can access the after completing the course.
Yes.
As long as you enroll even the assignment and the assignment and solutions. Okay, so the answer is yes. You can access the content as well as the assignments and the solutions, even in future. So let's say you take the course now, you are answering all the assignments, and or therefore you have enrolled, and therefore you have access to those assignments and you have access to those solutions. Then your login ID still remains valid. In future also, even though this course will get over in another month or so, the course will complete, and all the activities of the course in this run will get completed. But you will have access to the site. You can go in and you can see all the assignments. You can see all the solutions. It will be available for you for as long as you wish. Yes. So I think you have a clarification on how the exam is done. It is a computer-based exam. So you will come to a location. You will show your ID card. We will give you a hall ticket. Everything. You come there. The questions will be on the computer and answers will be. Oh, you're most welcome. We saw it's a thank you from Tirumala. Yes, you're most welcome. We are very happy that it's something that you can utilize whenever you wish. Yes, so we'll mostly have fill in the blanks, multiple choice, true or false, all those kinds of things will be there in the exam, and problems, which, like I said, it won't be pen and paper. You will have to work out the problem. There will be an on-screen calculator which you can use to work out the problem. When you're done, you have to enter the answer in a multiple choice mode. So that's the thing that we'll have to do. So yes, Anand Bhushan. So you have to send an email to nptel@iitm.ac.in. So if you do that, we can check on your I think your enrollment status. Right? Is that was your question? Yes, you had a question on your that you wanted to register, but it said you're not enrolled for any course. So you please send an email to nptel@iitm.ac.in with that with your details. If you send that, especially your login ID kind of thing, you send that in, and the Gmail ID that you have enrolled using, then we can check it out. We can figure out if there's an issue, and then we will sort it out for you. In the timing wise, what's the? We were almost done. No? Okay, so I think if you don't have any further questions, we will halt this session now. I hope you found that interesting and useful. அப்புறமா கூட இன்வோல்வ் பண்ண போறோமா நம்ம எப்படி இல்லை நம்ம we are going to do a subsequent session also. That will one. Okay, so we basically are concluding this session at this point in time. Feel free to keep asking questions. Feel comfortable to ask questions on the forum. As many as possible, I'll answer. Some of them, I mean, again, I'll also have to go look up the information. In fact, I always found that very useful. Even in my book, I say that many of the points that I have explained in detail in either the course or in the book are a direct result of students pointing out something and saying, I don't understand that. And if I look at it carefully, maybe I also don't understand that. Then I have to go figure out that detail and explain it clearly. So a lot of clarity in the book comes from that, from the kinds of questions that people have asked, doubts that people have raised. So please feel free to keep raising questions. And some questions I'll be able to answer immediately. Some I might need to look up. Some may be a little bit out of the scope of that course. But we will try our best to keep you updated. So I think with that, we will conclude this live session. I hope you enjoyed it. I think in all our courses, we are trying to do this. Please feel free to encourage your friends to participate in any live session that they have in their respective courses. They can directly interact with us. Thanks, Pushpendra. We are happy that this is of interest to you. So I think we will conclude this session now. Thank you.